Welcome back, ladies and gentlemen. Here in this video, we're going to be talking about a couple new ideas, specifically work and energy, as you can tell. But as is usually the case, these ideas have very specific meanings for us in physics, meanings that are probably at least a little different than what you're used to thinking of when these terms come about. First, I want you to recall that when there's a force acting on an object, so it doesn't matter what the object is, if you have a force acting on that object, then that object will accelerate according to Newton's second law. So an acceleration is proportional to the force acting on the object and inversely proportional to the mass of the object. So the stronger the force, the stronger the acceleration that that object experiences. And basically that is Newton's second law. As the object accelerates, though, it's going to be moving through a distance. So the force is going to push, and we have this motion, and the object may end up in a new location. And there will have been some distance traveled. And usually we do a delta D for that. And it is from there to there. And that's fine. And the thing is, though, we have this object, and the object is accelerating, and it's moving a distance, and it would have had some initial velocity here. We don't necessarily know what it is. It might have been 0, might have been something else, and it will have a new velocity here, a final velocity. And so there's a change in velocity because there's an acceleration. And so if we look at this, we can say, you know what, with these guys, there's an equation that we have. Of course, it's an old one. We have used it a whole bunch. So to link these things together, we usually would use this equation. So we're used to that. That's one we've used quite often. But how can force be linked to this? Well, it's actually pretty simple. We already have the idea right here where acceleration is equal to that. What we can do is simply make a substitution here in our equation. And so we're trying to figure out how force can be sort of incorporated into this, so we can look at how velocities change, how distance is traveled, and also look at force, having force in the mix. So here we go. I'm going to also do some rearranging because there's something special about looking at the force and the distance. So I'm going to isolate that. So watch this. First, just the substitution. And here it is. Substitution, force divided by mass. So that's all I've done is I've replaced acceleration with force divided by mass. And that's fine. Now what I want to do is I want to rearrange this, and I want to have the force and the distance traveled both on one side. So when they're shown like this, these two quantities end up being multiplied together. And so that means, well, I'll have to subtract VI from both sides. I'm sorry, VI squared from both sides. And then I'll have to divide both sides by 2. And then I'll have to multiply both sides by m, by mass. It ends up, and I'll just because I feel like I'm going to move the force and the distance over to the left side here. So on the other side of the equal sign, I've got final velocity squared minus initial velocity squared. And I have divided by 2 and multiplied by mass. So mass, final velocity squared minus initial velocity squared. And I have divided by 2. And this is not usually the form that it takes when you're going to see this equation. It's going to look a little different. So I'm going to simplify this a bit. Basically, dividing by 2 is the same as multiplying by 1/2. And we're doing that to the mass. We're doing that to the final velocity. And we're doing that to the initial velocity. And also, the mass is being multiplied by both of those terms. And so I'm going to sort of separate these two out. So we have the dividing by 2 and the multiplying by mass on the final velocity squared, and we have the dividing by 2 and the multiplying by mass on the initial velocity squared. So there we go. That's how we usually will see this. And so this is an interesting thing. And we sort of, you might be saying to yourself, aha, I see a delta V. There's a final minus initial velocity. Sort of. Sort of. But it's not quite so simple. Not complicated, to be sure. We're going to look at this equation. First, we'll look at the left side and talk about that for a minute, and then we'll look at the stuff on the right side after that. So I'm going to rewrite that up here real quick. Okay. And on the left, here's what's going on. We have this this stuff that's happening. This side describes something that was done to the system or done to the object. There was a force applied to the object, and the object moved a certain distance. Oh, I got rid of the delta. Sometimes we can write it, sometimes we can leave it out. I know that in your book, when you see this stuff, they leave out a delta symbol. And that's fine. It's just D for distance. No big deal. But this is stuff happening to the system. The force was exerted while the object moved this distance. So this side actually represents something. It represents the work done, I can spell, on the system. And so that's what we say. We say, well, work was done. A force was applied while the object moved a certain distance. Okay, now, because of this, we can see that, well, work, capital W, is simply equal to force times distance. That's an equation you're going to want to be able to recall and use. And of course, it's quite easy. When the force acts on an object while it moves, we say that work was done on the object. Okay, fair enough. So back to the equation, though. What about the other side, right? What about this business? And we're talking about it down here. So this side represents a property of the system, or a property of the object that changes due to the work that was done. So the work was done and some property changed. Yes, there was a change in velocity. However, there's more going on here. It's not just a final minus initial velocity. The velocities are squared, we're multiplied by mass. And so there's something else. So down here, I just want to look at it very generally. This idea of 1/2 mv squared. It represents something called kinetic energy. Now, there are many forms of energy. Kinetic energy is essentially the energy of motion. So we have motion here, there's velocity, and there's an object. All objects will have mass. So anything that is moving will have kinetic energy. All right. And so we usually say Ke, or sometimes just K, but Ke is 1/2 mv squared. That's another equation you want to be familiar with and be able to use. So the kinetic energy depends on the amount of stuff that is moving, that's mass, and on how fast that stuff is moving, that's your velocity. Or your speed, I guess. You could use speed as well. So now what we're going to do, though, is we're going to substitute in kinetic energy for each of those two terms in this equation. And we're going to substitute in the work for this business over here. We'll write a W. And so this initial equation will look simpler. There we go. Work is equal to, well, here this is final kinetic energy, and this is initial kinetic energy. And now we can very straightforward say, well, we have a final thing minus an initial thing. A final minus initial, this is a change in kinetic energy. When you do work on an object or on a system, then you will change the kinetic energy of that object. That is also a very important equation. Very important. In fact, it's very powerful, very useful. You'll see that as we start to analyze some situations using this equation. So in other words, the amount of work done on an object equals the amount of change in its kinetic energy. And if you know the object's mass, you know the force applied, you know the distance it traveled, and then you can find an amount of change of its kinetic energy, and you actually could find a change in its velocity as well. So let's look at this, though. This idea, these new concepts. Well, how are they measured? What are the units of these things? So that's what we're going to check out. Let's look next at the force times distance side of the equation. And when you have force that's measured in newtons, and you have distance measured in meters, well, that is just a newton meter. That's what we say, newton meter. But we usually will convert this to joules, capital J, or if you write it out, you don't have the capital, a joule. And so here's how this works. I'm going to break this down because it's worth checking out. A newton is a kilogram meter per second squared. That's a newton. And of course, a meter is just a meter. And so when you do this multiplication, you get kilogram meters squared per second squared. Okay, so I'm going to come back to this in just a moment. But this is still just a joule. 1 joule. Well, what about the other side of the equation? So we're going to look at the kinetic energy side. Make sure I keep this a little bit nice and organized for you. So kinetic energy is 1/2 mass times velocity squared. Well, the 1/2 has no units. Mass has units of kilogram. Velocity squared, well, that's meters per second. And that's all squared. Fair enough. But so that ends up being meters squared, and that ends up being seconds squared. And kilograms is multiplied to that. So you get kilogram meters squared divided by seconds squared. Whoa. Same thing. And so this is also equal to a joule. And so you should see this in any equation. When you equate things, they have to be equal both in quantity and the number that you get, and also in the units. The units have to match up. Otherwise, they don't equate. Okay, so what we say is both work and energy are measured in joules. That's what we say as far as units go. Joules. So next, it's probably very worthwhile to check out some examples. All right. Let's look at an example. I'll call it example number 1. Let's say we have a rock climber. Wearing a backpack. I'll say with backpack. Yep, I can spell. There we go. With a backpack of mass 7.5 kilograms. And the rock climber is scaling a cliff, so climbing a cliff. Then after 30 minutes, the climber is let's say 8.2 meters above the starting point. So 8.2 meters higher. Okay, so already we have a lot of information. We have a mass, we have a time, we have a distance, and this distance is in the y direction. It's a vertical distance, but that's fine. We want to know, let's answer a couple questions. Number 1, or part A. How much work does the climber do on the backpack? So we want to know the work done on the backpack. And part B. If the climber weighs 645 newtons, How much work does the climber do lifting herself, I guess it's a girl, lifting herself and the backpack? So we want work done on climber plus backpack. So in both cases, we're asked to find work. Okay. A is actually straightforward. Here we go. There's more than one force acting on the backpack. So a little free body diagram here, right? And the backpack has weight, and the backpack is being somehow pushed or pulled up by a force from the climber. The thing about this is, really the backpack is not accelerating anywhere, so I can reasonably say that the forces are equal. Forces are balanced, so it's in equilibrium, no acceleration. But what we're trying to figure out is the work that the climber does on the backpack. Work on the backpack, I really should specify. Work done by the climber. Sorry about that. It actually does matter. Work done by the climber. And that's this force. And the reason is the work done by gravity is going to be slightly different. Let's not worry about that right now. We only have to worry about the force that's in question, the force applied by the climber on the backpack. Well, work is equal to a force times a distance. And it sure looks like we can easily figure this out. How much force is the climber exerting on the backpack? What is this equal to? Well, that force is equal to that force. And that force is just mass times gravity. So that means so is this one. And so that force is mg, and we multiply by a distance, we can find the work. The mass of the backpack was 7.5 kilograms. G is 9.8 meters per second squared. And the distance, 8.2 meters. That's supposed to be 8. So looking at this, I should get a kilogram meter squared per second squared. That's how I can check that I've got it set up right. The units all work out. Okay, so I do this math, and I get right around 603 joules of work on the backpack. I have an answer for part A. Pretty straightforward. So remember, I wanted the work done by the climber, so I simply focused on this particular force, because that is a force exerted on the backpack by the climber. Okay, so next I can look at part B. If the climber weighs 645 newtons, what's the work done on the climber plus the backpack? Okay. So from the previous problem, here's part B. So I have several forces taking place. I'm simply going to consider the backpack plus the climber to be the same object. So that means there's a weight here on that one object, force due to gravity. And just like before, well, there's no acceleration. The climber isn't speeding up. But there is a force in the upward direction to get the climber up the cliff. Okay, but here's the slightly, I don't know if I want to say tricky, but thing you have to pay attention to. The climber weighs 645 newtons. Well, what does the backpack weigh? The backpack weighs that mass times that g, mg. And so the weight of the backpack you get 73.5 newtons. So here's the deal. I need to figure out the force acting on the climber plus the backpack, this guy. It'll be equal to that. But that weight downward is equal to the weight of the climber plus the weight of the backpack. Those two weights combined. So 645 plus 73.5. So this guy is 645 newtons plus 73.5 newtons. Well, that means, so was that. But I can figure out the answer down here. 718.5 newtons. So that means this force is 718.5 newtons also. And so I have weight of climber plus weight of backpack gives me the total weight. And the two forces are equal because things are not accelerating, not speeding up as the climber goes up the cliff, just going at a constant pace. So I know that force. And with that force and that distance, I can find the work done on both of these guys. So the work done on the climber and backpack. Well, this is going to be that force times the distance. That force is 718.5 newtons. And that distance is still the 8.2 meters. So the work done, I'll fill that in for you. The work done is your force times your distance, and $5,891.7 joules. Okay, so here's the issue. The numbers in the problem with the least number of significant figures really are these guys with 3 sig figs, and that guy with 2 sig figs. So I really want to round this a little bit, just because I don't know the 1 or the 0.7. I don't know those that accurately because I didn't know the other numbers that accurately to that many sig figs. So really, I can call this 5,000, really close to 5,900 joules. So if you don't like that much rounding, okay, that's fine. But you get the idea. You get how to work this out, and that's the whole idea: how to calculate the work done. Well, all right. So notice something: the work done on the lifting the backpack or the backpack plus the climber didn't change the kinetic energy of either one of them. This is because the lifting forces weren't the only forces acting on them. So if there were no weight, if that was the only force acting on the climber and the backpack, then that force would have done work, and that work would have changed the climber's kinetic energy. The climber would have been speeding up. But because this force also exists, there was no change in the climber's kinetic energy. That's important to realize. Okay, another example. I'll start on a fresh page here. And this example will wrap this up. Example 2. You apply a 100 Newton force to a shopping cart that has a mass of 50 kilograms. It's got some stuff in it. Shopping cart of mass 50 kilograms. If the shopping cart starts at rest, so initial velocity is 0, starting at rest, what is the kinetic energy after it rolls for 2.5 meters? So we want to know the kinetic energy, and we are given that it rolls 2.5 meters. So here's the thing we're looking for, and we know the force that you're applying, and we know the mass, we know initial velocity, and we know distance. We do not know final velocity. That's fine. We can work this out. So here's another way of looking at work and kinetic energy now. This force will change the kinetic energy of the object because with a good shopping cart, there's really very little friction, and there's no force opposing this. As there was here, there's a force opposing that one, so they cancel out. Here, there will not be. So basically, shopping cart, I don't know how to draw one very well. So, I don't know, wheel, handle. Okay, you apply your 100 Newton force, and shopping cart travels a distance there of 2.5 meters. Your initial velocity is 0. What we want to know is, what is its kinetic energy after it rolls? So we want, at this location, the kinetic energy. That's our goal, right? That's a terrible question mark. There we go. Okay. Well, because I try to be good at physics, I'm going to do the whole free body diagram thing. The force is acting on the shopping cart. Of course, you have your 100 Newton push, and right. But the cart also has its own weight. I don't know how long to draw that arrow, but there's a weight. But the thing is, there's a normal force. The floor is pushing up on the cart, and I know that that should be equal to the weight. I know that it should be equal because there's no acceleration up or down. The cart is not accelerating down into the ground or up into the sky, so there you go. These two cancel, and that's the only one left uncanceled. All right, well, I know that work is equal to change in kinetic energy. I'm going to start there. I know that work is a force times distance. And I know that change in kinetic energy is equal to final kinetic energy minus initial kinetic energy. So an important thing to think about here is, well, my initial velocity is 0. There's no motion at first. So if there's no motion at first, your initial kinetic energy is 0. Equal sign, sorry. So the equation gets a little simpler. And I'm looking for this guy. That's the answer I want to find, the kinetic energy after it rolls 2.5 meters. And I have my force, which is 100 newtons, and I have my distance. So I can work this out. I should do 100 newtons. And my distance is 2.5 meters. And this is equal to my final kinetic energy. So real simple, I just move the decimal point and I get 250 joules. That's the answer. That's it. Okay. Now, there's a sort of a supplemental thing here. I've answered the question, but kinetic energy, you know what? You can't see energy directly. When the shopping cart is here, what do you see if you're looking at it? You see it moving. You see its motion, and motion is velocity. So one final thing to look at here is, well, once it gets to this point, how fast will it be going? Right? So we can use this simple relationship. We know the amount of kinetic energy. We know the mass. We want to find that velocity. So I'm going to rearrange this to solve for velocity first. Okay. So velocity is being multiplied by 1/2, so I'm going to divide by 1/2, which is the same as multiplying by 2. Multiply both sides by 2. Cancels that. Now I'm multiplying by mass. I have to divide both sides by mass. And it cancels that. This is velocity squared. I have to square root both sides. Square root the whole thing, all under the radical. And it cancels the squared, and I have my velocity. Let me rewrite this for you. Velocity is equal to 2 times the kinetic energy divided by the mass. And that's the equation I can use. So 2 times my kinetic energy was 250 joules. That's a J. And the mass of the shopping cart was 50 kilograms. And when I work this out, we should be traveling at 3.2 meters per second. That should be the velocity. And so really this is the final velocity, right? Because I was using final kinetic energy. Now I know how fast it was going because I knew how to find that final kinetic energy. Pretty awesome. And what you are likely to realize as you get more involved with using work and energy, is that the equations are actually easier to use than some of the old equations. It's easier to find certain answers in certain ways using work and energy than it was using just velocities and distances and times and accelerations. Okay. So that's it for now. This was page 7. Sorry. So, okay, now that's it for now. Thanks for watching. I'll catch you next time.